Hi everybody, welcome to this lecture. We're going to cover the essentials of object-oriented design, and then we're also going to look at the implementation of a simulation for which the source code has been provided. So when you get to the second half of these slides, you might want to simultaneously take a look at the provided simulation, which is called Prairie of Prey. And the provided code includes, I believe, several class definitions, some of which are defined in the context of others. So you should definitely download the provided code to experiment and also get a feel for inheritance relationships, which is really the essence of this lecture. So while object-oriented design relies upon traditional imperative constructs, the emphasis in the former, or object-oriented design, includes the possibility of defining custom types. And custom types are referred to as classes. So in any given domain, what some folks call the problem, the implementation is structured utilizing objects to perform automation. A class enables functions, sometimes called methods and attributes, sometimes just called data or fields, to be bundled together in a single unit. If one is building a simulation of some kind, it isn't difficult to imagine how class definitions might be utilized to model entities. And these entities are programmed to interact. Each entity maintains its own state. One entity may affect another by invoking its methods, and methods typically impact an entity's state. The definition of an entity is equivalent to the specification of a class. Once a class is implemented, it can be utilized to instantiate objects. And instantiation is the process of allocating memory. Memory allocation results in the creation of an object. An object has a reference or address, a place in memory where the object resides. Once classes are defined to represent entities in the simulation, it is possible to create objects. It also makes sense to define a class representing a space in which the objects may interact. And this space might just be an array or a set of key-value pairs. Utilizing an array to hold objects required special treatment, as we'll see in the example. A class hierarchy is structured similarly to a binary tree. Class definitions may exist in relation to each other. The class at the top of the class hierarchy is referred to as a superclass. The classes which appear at the bottom of the class hierarchy are defined as subclasses. The advantage to being able to define classes with respect to each other leads to a less complex as well as easier to understand simulation. A superclass contains attributes and methods that all of the classes in the hierarchy share. A subclass is a variation on the superclass. A subclass is a specialized version of the superclass. Each subclass is a refinement of the superclass. A subclass contains the attributes and methods defined in the superclass. A subclass contains attributes and methods that are not defined in the superclass. Methods may be further specialized in each subclass. Such specialization is classified as method overriding. In some situations, specialization may be achieved by overloading. A subclass may include a method having the same signature as a method defined in the superclass. When this method is invoked on an instance of the superclass, the method defined in the superclass is called and executed. When this method is invoked on an instance of a subclass, the method in the subclass is called and executed. Overriding is an example of the polymorphic behavior inherent in class hierarchies. Polymorphism enables treating an instance of a subclass as if it were an instance of the superclass. It is possible to define an array to index instances of the superclass and to allocate memory in the array for instances of any one of the subclasses. While the array is defined to index instances of the superclass, the array may hold instances of any one of the subclasses as well. We say that the subclass is a superclass. So here we get into the implementation of simulation, and along with the simulation is a class that contains the main method that provides some simple graphics. So we're not really going to place so much an emphasis on that side of the implementation. We're going to focus more on the simulation side of the implementation. And so if you look at the provided code, you'll notice an object of the simulation is declared in the class that implements the graphics. And so you can think of the simulation class as kind of being the brains in some way. And you can think of the graphics class as being what everything looks like. And so if you look at the simulation class in the provided code, you'll notice these imports are made. And so we're importing random to generate random numbers. We're importing image IO to be able to import ping images. We're importing buffered image to be able to save images. And we're also importing file to be able to create a reference to the pictures that we load, which are essentially avatars of each of the types of creatures which are present in the simulation. And here you can see we have attributes. These are actually attributes of the simulation class. We have an array of creatures. We have a size of 5, which is the size of the creature array. We have a random object. We have an int called rval, which we're using to hold random values. And we also have some constants, box height, box width, and also pick width and pick height. And these are pretty well self-explanatory. Box width and box height are the x and y values of the size of the screen, which we're using to render graphics. And pick width and pick height are the x and y values, or the size of the 3 images we're using, one for tiger, one for python, and one for zebra. And here you can see the constructor, and in the simulation constructor we're simply allocating memory for creature objects, and there are 3 subclasses of creature: zebra, tiger, and python, and we're using the random number generator to randomly populate the prairie with 5 creatures. And the creatures that are actually populated depend on the outcome of these calls, or this call here, to rand nextInt. And here you can see some methods of the simulation class. We have getCreatureImage, which receives a subscript and returns the image at a specific subscript in the underlying prairie array, and the prairie array is an attribute of the simulation class. We have getSize, which simply returns the number of elements in the prairie array. And we also have getCreature, which simply returns a reference to the creature at a particular subscript in the underlying array of creatures, which again is called prairie. And here you can see we have attributes of our creature class. We have a buffered image, and we are saving the avatar of each of the creatures in this attribute. We have xCord Y chord, X speed, and Y speed, and these are pretty well self-explanatory. And notice that each of these attributes is protected, which means subclasses of creature inherit these attributes. Here we have some methods of our creature class. We have getImage, which simply returns the image of a particular creature object. We have setCoordinates, and this method is kind of important because it determines where the creatures are placed within the prairie when the simulation is initiated. And you can see we're using the random object to generate integers in a range of legal values. So we only want to select coordinates which actually fit somewhere inside the screen. And here you can see we have our getter methods. We have getXCoord, getYCoord, getXSpeed, getYSpeed, and these are fairly self-explanatory. These methods simply get the value particular attributes, the value of particular attributes assume, and this enables us to update the position, this enables us to retrieve the X and Y position and also the X and Y speed of a creature object. And here you can see the setter methods for the creature class. We have setXCoord, setYCoord, setXSpeed, and setYSpeed. And these method names accurately define what the methods are being used for. And we can use these methods to update the position of a particular creature and also to set the X and Y speed of a particular creature. Here we have our first subclass. Zebra is a subclass of creature, and you can see we've defined a constructor, and we're simply loading the ping image, and we're setting X speed, we're setting Y speed, and we're also calling setCoordinates, which uses the random object to generate initial random coordinates on a random basis. And here you can see we have tiger, which in many ways is similar to zebra, with the exception that the tiger moves more quickly than the zebra. So we have X speed and Y speed for our tiger. We also call setCoordinates, and this determines the initial position of the tiger. And you can see in the constructor, we're loading the picture which represents the tiger. And here is our Python subclass, also extending creature, and we're loading, in the constructor, we're loading a picture of the Python. We're setting X speed and Y speed, and we're also calling setCoordinates, which again determines the initial position of this object in the simulation. And this is basically what we end up with. This is a screenshot of the sample code that is available in Canvas. This is the simulation actually running. And if you get it up and running, you'll notice there are definitely some enhancements that can be made. And that's something you can work with. This isn't actually an assignment for this class. It's really just meant to give you a feel for the way superclass-subclass relationships can be used to define objects which are similar in some ways and different in others.